All right, here we go. Chapter 8, Similarity. This chapter, this unit on similarity, is another geometry unit, and it's very, very closely tied to a unit that was part of your Math 1 course last year. In Math 1, one of the geometry units you did, probably second semester, dealt with what are called transformations. Essentially, a geometric object in free space or on a coordinate grid, as it's moved or changed in some way, we call that a transformation, simply put, right? Any change in position, shape, size, whatever it might be, those are called transformations of that original object. And where that change happens or where it ends up is what we call its image. Just as a little bit of a refresher on that. So again, you had an entire unit on it last year. You will be able to float this if you don't remember anything from it. But for right now, I'm just going to be kind of rehashing some of the terms that we learned in there. And in that unit from last year on transformations, you learned about 3 specific types of transformations. And there was a reason why they chose the 3 that they did for that unit last year. And the 4th of those transformations is actually what we're going to be covering here in this section today. So I'll first talk about the 3 that we covered, that you would have covered in Math 1. Okay. And then I'll talk about how that's related to this one here today and why this one is separated out from that bunch. All right. So the 3 that we learned in transformations in Math 1, I'll make sure I go into more detail into those in section 2, where we're going to be talking a little bit more of these combinations and stuff. But the 3 that we covered, you'll probably recall the names as I go through them, or at least be familiar with some of them. The first one you would have learned about is called a translation. Essentially, you take some geometric object, keeping it exactly oriented as it is, and simply sliding it somewhere else in free space or on a coordinate grid. Okay, translation, just sliding an object around. All right. The second one you would have learned would have been reflection. Now, reflection, the term itself is probably a little more familiar to you. You can think of a mirror and how it reflects your image. But essentially, a geometric object in free space or on the coordinate grid, if it's being reflected, it's literally being inverted or reflected over some line of reflection that may be useful to think of as a mirror of sorts. Okay, and the reason I use that term inversion is because if you think about it, if you were to look into a mirror and wave at yourself with your right hand, even though you physically are waving with your right hand, your image or your reflected image in that mirror, if you were to kind of think of that person's perspective, it would be their left hand that would be waving back at you. So it essentially inverts the image over a reflected surface. So again, in terms of our transformations that you would have covered in Math 1, it simply reflects it like a mirror would over some line of reflection. And the third one you would have learned about would have been one called rotation. Kind of like the clocks in a clock, the hands going around a clock. You would take some object and rotate it, keeping its orientation and stuff, but rotating it about some center of rotation. Okay. Now, the reason why those 3, translation, reflection, and rotation, are grouped together in Math 1 is because they are what we call congruence transformations. Whatever the object may be, it keeps its exact same dimensions. It is completely congruent to its original object. Wherever the original was to wherever the image ends up, they are completely the same object as if they were cut and paste from one to the other. Okay, they're congruence transformations. The reason why this section on dilation was not part of those transformations is because fundamentally what will happen here is that these 2 shapes will not be congruent to each other. Okay, and that leads me to the name of our unit, which is similarity. So similarity fundamentally is different than congruence. Congruence means literally again, copy and paste. It is the same dimensions. Every measurable aspect of one object is exactly equal to every measurable aspect of its image or its congruent partner. Similarity is different. But built into the word is that word similar. Okay, so there's definitely going to be some relation between an original object and its image. And in this case, what you can kind of see represented here is my original triangle, and there is its larger image. You can see that it's what we would call a scale model of one or the other. Okay. The angles inside of that triangle are going to be the same angles, whether it's small or big. You can kind of see the same kind of ratio of sides. That's why it kind of looks the same. And many of you have seen scale models of things before. The one that's probably most familiar to you would be like toys, right? Namely Hot Wheels. Many kids play with Hot Wheels cars at some point in their life, but they're essentially scale models, scaled down, minimized models of the real vehicle. And the reason why kids like playing with them so much, like my son likes playing with them so much, is because it's like they're the real vehicle. It's just a miniature version of it. Okay, if it was out of proportion or not to scale, it would look weird, right? Wheels might be too big, or like if you were to like the windshield wouldn't look right on a car compared to what it would look like on a real car. There are lots of different ways you can mess it up, but it's typically pretty noticeable when you have like a model of some real object and it's not to scale. There are some noticeable differences. Okay, and we call that in geometry, in mathematics, similarity. If it is completely scaled down or scaled up appropriately, it will look like the original object, just a larger or smaller version of that object. Okay, and so again, we call that in geometry similarity. Not congruence, because fundamentally, if you were to hold up a Hot Wheels Dodge Viper up next to a real life-size Dodge Viper, it's quite obvious they're not congruent, because the Hot Wheels car can fit in your hand. You cannot definitely hold a real Dodge Viper in your hand, right? So they're definitely not congruent. They are what we call similar. And a lot of baggage comes along with that, and that's what will be explored throughout this unit. But let's talk about the transformation that makes similarity possible, and that is dilation. All right. The formal definition of dilation, and again, I'm not going to test you on what it is or anything like that, but just to kind of hear what it is, it's a transformation or a change or movement in which a figure is enlarged or reduced with respect to a fixed point that we call the center of dilation. Okay, so in this case, that center of dilation C is right here. Depending on where that center of dilation is located in the universe, it will affect where the location of the image will be located. Whereas how large or how small the image gets is a function of what we call scale factor. So dilation will fundamentally enlarge or reduce the size of some object, thus making two things that are not congruent. Okay, it's not like the congruence transformations that we had in Math 1, but they will be similar in size, similar in shape. Okay. So one other quick thing to point out here in the diagram that you see on your screen, just to kind of refamiliarize ourselves with this, you'll notice that I have point P, Q, and R. This is what we would call the original object, triangle PQR. I know this is the original because of what the points are titled. Point P would be the original point P. In other words, it's where it's originally located. When I add in these apostrophes, so for instance, P prime, we call those apostrophes primes, it still uses that letter P to show me that this is a corresponding point. It's still that top corner of this triangle. But the prime tells me that that's where its image is located. Okay, for instance, P, the original P, is where it's originally located. P prime represents where it has moved or changed to based on whatever transformation has happened. So when you see the images, you'll notice the apostrophes next to them. Okay. Most of the stuff on Big Ideas will also use some sort of color coordination, like blues versus pinks and stuff like that. But again, one quick way you can check it, the notation will use these apostrophes to denote that this is the image. And if it moved again and stuff like that, I would just keep adding apostrophes to show like the order of that movement. We'll explore that a little bit later in this unit. Okay, so I have original triangle PQR that has been dilated or magnified over here to P prime, Q prime, R prime, its image. So it has enlarged in this case. So let's talk about how to measure how much larger the images or smaller the images, depending on what kind of dilation has been performed. That measurement is performed by something called scale factor. All right, so we measure this using a term called scale factor. And again, if any of you are familiar with models, if you've ever put together like plane models or house models or model trains and all that kind of stuff, you'll be familiar with the term scale modeling, right? Scale modeling refers to the fact that there is what we call a constant scale factor. Many of us at some point have seen like model cities or miniature versions. Many of us have seen like miniature trains and little like miniature shops and stuff like that. And when it comes to like toys and stuff, there are tons of brands out there that do scale versions of real life objects. Okay. Tough to call Barbie a scale version of real human beings. I don't know if you've ever seen this thing on social media and stuff like that, but if you were to actually scale up the size of Barbie to a real human being, that human being would look alien and terrifying. Okay, no human being has those real dimensions, right? Whether it be Disney princesses with oversized eyes or whatever it might be. Okay, but there is something fundamentally wrong, and you can definitely tell a difference when something is a real scale version of something real in real natural life versus something that has been animated in some way, shape, or form to enhance certain things. Okay, so this term scale, for when it comes to modeling or toys, whatever it might be, refers to scale factor, and in math we give it the term K. Okay, so some scale factor K. The factor part, well, it should be familiar within mathematics as well. Factor means that we're dealing with a constant multiplier. So when I talk about a scale factor, every measurable aspect of, depending on the dimension, every measurable aspect of the original object is multiplied by something to get to its image. So for instance, the length of P to R, this simple side right here of my triangle, would be multiplied by some constant scale factor to get to P prime R prime. And whatever that constant multiplier was would be the same multiplier I would multiply by, say, Q to R as Q prime to R prime. A constant scale factor for the entire object. And so how do we find out what that scale factor is? Okay. This is the formal way to express it. Again, I can kind of reduce this down to a more abbreviated version. Essentially, it's going to be distance to the image over distance to the original. Distance to the image over distance to the original. Okay, or another way to talk about it would be the size of the image over the size of the original. Essentially, we make a fraction, a ratio. Okay, and we're comparing two things, the image on the numerator to the original object on the denominator. Okay, so for instance, in this case, if I were to actually count the units from my center of dilation C to my image point, P prime, I could do the same thing to Q prime or R prime. P prime is just nice and convenient because it's just counting the boxes in this case. But if I were to count those boxes, those units, I'd find that this is 8 units away from the center of dilation. 8 units to the image. There are only 4 units to the original point P. Okay, if I were measuring to Q prime, I would go to Q prime and then Q. If I were measuring to R prime, I'd go R prime and then R. But let's stick with P. So P to P prime, right? Distance to P prime is 8 units. Distance to P is 4 units. So my actual ratio, my scale factor would be 8 over 4. That reduces to 2. So my scale factor here is 2. What does that literally translate as? In other words, my image is 2 times the size of the original object. So if I were to actually take out a ruler and measure the side length from P to Q and found it to be, I don't know, 2 miles long from P to Q, that would mean that I would, in order to find out what the distance was from P prime to Q prime, I would take that distance and multiply it by the scale factor of, in this case, 2. So 2 miles would become 4 miles. Okay. Or if this was 7 miles, that would be 14 miles. If this one was 5 miles, that would be 10 miles. Okay. You kind of get the idea. Scale factor is a constant multiplier. In the margin here, a couple quick facts about scale factor. Again, looking at these diagrams, the original objects and the images, it'll be pretty apparent really quickly when it's enlargement versus reduction. Just by simply looking at it, we can quite obviously see here that the original triangle is much smaller than its image, meaning that this is an enlargement. But mathematically, we can just analyze the scale factor k as well. If k is bigger than 1, much like this 2 is bigger than 1, then it will fundamentally enlarge from the object to its image. And that makes sense because, again, if we're talking about a constant multiplier, if I multiply it by something bigger than 1, like say 2, I will fundamentally make those numbers bigger. In this case, twice as big. Whereas if k is between 0 and 1, whether that be a decimal or a fraction that's less than 1, then it will fundamentally reduce or minimize the size of the image. Okay, so if, for instance, my scale factor was 1/2, 1/2 is less than 1, and that would make sense because if I'm constantly multiplying by 1/2, that means it's getting smaller with every multiplication. Okay, so let's see how this would look in terms of our problems for this section. Okay, so here's our first example for the chapter. You're going to be seeing diagrams like these guys, okay? And a lot of information is going to be on them, but these will actually be very fast for how we'll end up solving these problems. So here we're given the following diagrams, and we're asked to find the scale factor of the dilation that's being shown. So our job here is to identify k. Okay, not just whether or not it's getting bigger or smaller, but to actually measure how much bigger or how much smaller the dilation is that's happening. Okay, so for instance, in this case, it'll be quickly apparent that my original triangle right here, denoted by this simple p, versus the image of that triangle over here, denoted by p prime, or that p apostrophe, it's quite obvious in this case that this is an enlargement. Okay, so that's simple enough, but scale factor measures how much larger it gets. Okay, and that will be denoted by some sort of ratio between these measurements right here. Namely, here's the center of dilation. It going to its image point up here is 12 units. 12 units to get from my center of dilation to that image, versus only 8 units to get to the original point. Okay, so this will actually end up being pretty similar to the one we did above, and I'll deal with this on the whiteboard in a minute. Over here, we get kind of the reverse of it, where now my original object, my original square, is this blue guy here, denoted by the just plain P right here. And then my image of that square is the smaller one right here, denoted by that P prime. So this one is quite obviously a reduction or a minimization. But again, when I use scale factor, now I'm actually measuring how much smaller it's getting. Okay, so let's jump to the whiteboard to actually talk about how to solve this. All right, so for part A, we were given the following. All right, so first off, our formula for solving this stuff, we're going to be dealing with scale factor, K. And that scale factor measures a ratio, a fraction, top to bottom. Simply put, we're going to be measuring the image versus the original. Some sort of image measurement over the original. In this case, we're measuring the distance from the center of dilation to some point on the image, and then comparing that to the distance from the center of dilation to that corresponding point for the original object. So in this case, for part A, the distance from point C, the center of dilation, to point P prime, prime being the image, ended up being, again, we're dealing with a ratio, ended up being 12 units. Whereas if I'm measuring from C to P prime for the image point of 12, going to the original, or just regular old P, if I were to look at that diagram, it told me that the distance from the center of dilation to that point P was simply 8 units. So this represents my scale factor. Distance to the image over distance to the original. P prime versus P. Okay, now this is a fraction that can be reduced, and that's really the mathematical aspect that we need to be prepared to do here for this section. So 4 goes into both top and bottom, so I can reduce this fraction. 4 goes into 12 3 times. 4 goes into 8 only twice, meaning that this is my reduced fraction, meaning my scale factor K for part A is 3 over 2. Now that 3 over 2, for the record, is bigger than 1. 1 in this case would be 2 over 2. So this is bigger than 1, meaning that this is what we would call an enlargement. Again, pretty apparent if you look at the actual diagram itself. It's pretty obvious that the image is bigger than the original, but worth putting here anyway. All right, for part B, it's the same exact solution process. I'm still measuring some scale factor K, given information on the diagram, and I'm still comparing the image versus the original. It's just that in part B, the image is smaller than the original. So we should see a reduction K value here. So when I identified this on our diagram, the distance from the center of dilation to the image point P prime was 12 units again. But now the distance from the center of dilation to the original point P ended up being a lot bigger in this case. It ended up being 30 units. And again, this is my scale factor. I just have to reduce the fraction. And 6 goes into both top and bottom. 6 goes into 12 twice. 6 goes into 30 5 times. So here's my fully reduced fraction. So my scale factor for part B is 2 over 5. Now it's worth noting 2 over 5 is less than 1. 1 in this case would be 5 over 5. So since this is less than 1, this is what we would call a reduction. Again, very apparent if you were to look at the diagram itself, the image is definitely smaller than the original. So that's kind of like a quick sanity check here. But that's how you would end up actually measuring what is K, or scale factor. Let's move on. Real briefly, one other point regarding those diagrams. Okay, in this case, we are measuring the distance from the center of dilation to the respective points. You could also measure, like, for instance, if they gave you 2 points here, if they told you, like, hey, this distance for this segment was, say, 18 centimeters, and then they told you the distance here to here was, say, 12 centimeters, then again, I would use my image distance as my numerator, and then my denominator distance as my original distance as my denominator. So that's just another way you could do it. In this case, we're measuring distance from center of dilation to the points, but some other measurement of that image versus the original can also work. All right, let's move on. So next up, we have this example. This is going to end up being kind of like the flip side of the same coin. We're going to use the same exact equation. We're just going to be given different information. So for this example, we are told this. You are using a 2.5x zoom on your camera. And notice that the image of what you're taking a picture of is 3 inches tall on your screen. So let me break that down really quickly. First off, 2.5x zoom, we'll all be familiar with this on our phones. If you've ever messed with your camera, you'll notice a little like zoom measurement there, whether it be bigger than 1 or smaller than 1. In this case, 2.5x zoom is a pretty common one for most cameras. It basically magnifies an image. So if what you're taking a picture of, if you were to zoom in on it, you could zoom to a 2.5x zoom. Okay. If you were to go smaller and say zoom out, that'd be like a 0.5 zoom or a 0.1 zoom or something like that. So in this case, we're zooming in, we're magnifying some existing object to make it larger on our screen. Okay, but we're taking a picture of something, and if we were to actually put a ruler on our screen and measure the image on our screen, it'd be 3 inches tall. okay, using that 2.5 magnification. The question here is, how tall is the image without the zoom? In other words, if I were to zoom back to the original just camera view, or another way to ask that would be, what is the size of the original real life object that I'm taking a picture of? Okay, so let's jump to the whiteboard to kind of go through the solution. So there's one important thing to kind of point out here at the very beginning. We were told this fact at the very beginning. I'm using 2.5x zoom. So for the record, this x is not some variable. This is actually representative of multiplication. In other words, it's telling me that I'm magnifying some image, some object I'm taking a picture of by 2.5 times. So what does this mean? For us, in terms of this section, that is literally a designation for scale factor, namely k is equal to 2.5. Because again, k represents some scale factor. Factor again means some constant multiplier. There's that multiplication symbol. So when I'm zooming on a camera and it says 2.5 zoom or 10x zoom or whatever, it's literally telling me what the scale factor multiplier is. In this case, my scale factor is 2.5. So I'm still going to use the same formula that we did in those last examples, that some scale factor k is representing some ratio, some fraction, where I'm measuring some image distance or image measurement versus the original, or whatever it is that in this case I'm taking a picture of. Okay, so this is still true. The difference here with this problem than that previous example is, in the previous example, I was given both of these measurements and had to solve for k. In this case, now I'm given k and I need to solve for one of these. So in this case, I know that k is 2.5. And it's still going to be equal to some fraction, some image distance over the original distance. And in this case, I'm being asked what the original size of the object it is that I'm taking a picture of, whatever it may be. Whereas I am told the actual image measurement. In other words, on my camera screen, if I were to measure the object, it's 3 inches tall. Okay. So just to kind of put this into more algebraic terms, let me get rid of this original object thing, and I'll actually put in a variable like, say, x. Okay, and so this 2.5 magnification, its image is 3 inches tall. I need to figure out how many inches tall the actual original object is. So let's do some algebra here. If I want to solve for x, let me pull it out from the denominator here, because this is where a lot of students make mistakes. I actually can't solve for x while it's in the denominator of a fraction down here. So let me multiply it up top, and we'll do some of our inverse operations here. So if I multiply x to this side, I'll end up with 2.5x. And that's going to be equal now that I've multiplied this up here, now I just have 3 inches, or just 3 here on the right-hand side. Okay, so again, first step here was to move this denominator over to this side by multiplication, because denominator is just another fancy way of doing division. Okay, now if my variable were on the numerator, I would simply have to multiply the denominator to the other side, and then that would just be a one-step problem. I went with this one because this one tends to be the one where people mess up on it. All right, so I've moved x out from the denominator. I still need to get x by itself. Okay, so in this case, what I'm going to do is I'm going to move the 2.5 by division. And so if I divide both sides by 2.5, I get the following. So don't be a hero, use a calculator. So 3 divided by 2.5, I get 1.2. In other words, the original object, the real life object, is 1.2 inches tall. Whatever it is that I'm taking a picture of, it's 1.2 inches tall. So let's just quickly sanity check that about what we were given. We're using a 2.5 zoom, and we're taking a picture of a 1.2 inch object. If it is being magnified 2.5 times, that means I would multiply this number times 2.5. Let's see what would happen if I get that. That means its image on my camera screen should be 3 inches tall. Okay, so that's how you can solve those problems if you're actually given the scale factor k. And again, this one was a trickier one because my variable was in the denominator. And that's how I would end up moving it. All right, let's keep going. One last problem to do for today's notes. Let me jump back to our, actually, let me scroll down here. Let me jump back to our notes. I'm actually going to also be referencing our solution sheet for this problem. Cover this up so we don't get distracted. There we go. All right, so several times throughout this unit, we're going to be dealing with coordinate grid problems. So you'll see several of these types of examples. You will be given either an object to graph or just explicitly given the object already on a coordinate grid graphed for you. And then you're going to be asked to perform a dilation of it. So in this case, I'm asked to graph the following coordinate points, K, L, M, N, so some sort of quadrilateral on the coordinate grid. Once I've graphed that original object, I'm going to dilate it or magnify it / minimize it based on a given scale factor. In this case, scale factor of 1/3. So just a quick sanity check here about like what I should end up with. Whatever object that it may end up looking like, I just know it's going to be some quadrilateral based on my coordinate points here. But whatever my quadrilateral looks like on the coordinate grid, if I'm using a scale factor of 1/3, the fact that this is less than 1 here would be 3/3. So the fact that this is less than 1 means that I'm going to be reducing the size of that object. Okay. Now over here in the margin, here's a little bit of a hint on how to do this on coordinate grids for dilation. Okay. So in this case, because we're dealing with constant factor or scale factor, we're going to be multiplying by something. All right. So for any original point that I have on my original object, say for instance, point K, -3, 6, if I'm going to dilate that point and move it to its new location, transform it or dilate it to some other location on the coordinate grid, how would I go about doing that? In this case, I'm simply going to be multiplying by my scale factor K. In this case, 1/3. So in order to find out the image of K, or where K prime is located, I would simply take this coordinate point -3, 6, and then multiply it by 1/3. So for instance, -3 times 1/3 would be -1. 6 times 1/3 would be 2. So my new point, K prime, would be at -1, 2. So let me jump to the solution sheet so you can kind of see this worked out. All right, here's our problem. All right, so again, we were asked first to graph coordinate points. Hopefully you're comfortable with that. We can see here that K at -3, 6 being left 3, up 6, there's K. L was at 0, 6, left, right, 0, up 6. M was at 3, 3, right 3, up 3. N was at -3, -3, left 3, down 3. So there's my quadrilateral, this kind of weird arrowhead looking shape. That's my original object. My job here in this problem is to dilate it using a scale factor of 1/3. Okay, that scale factor K of 1/3, again, because it's less than 1, should reduce the size of this object. And you can already see the end result here. Here's the image. And a couple things about it. First off, it makes sense that it's smaller because, again, K is less than 1. But also, I want you to notice how it is generally the same shape as the original object. It's just a smaller version of it. It should not look weird. It should not have like the image of M somewhere magically down here. It should not look like an entirely new quadrilateral in this case. It should be a scale model version of the original. In this case, it should just be a smaller miniature version of its original. So how would you go about doing it? Each of these points represents the original points. Here's K, L, M, and N that were given above. In order to find out where the image point is located, I would simply multiply through by the scale factor, in this case 1/3. So it's just a bunch of multiplication. -3 times 1/3 is -1. 6 times 1/3 is 2. This tells me the location of the image of K, or K prime. So -1, 2 would be left 1, up 2. There's K prime. L prime, I multiply 3 by 1/3. 1/3 times 0 is 0. 1/3 times 6 is 2. 0, 2 is L prime. There it is right there. And so on and so forth. Be careful about this. In this case, multiplying by 1/3 is also another way of just dividing by 3, just as a point of reference. Okay, but all we're doing here for these kinds of problems when I'm dilating on a coordinate grid is I'm simply multiplying the x and y by that scale factor k. Okay, and that's going to conclude our lesson here on dilation. I'll go ahead and stop recording there.